This is a tutorial on the natural base e. The natural base, or the number e, is an irrational number that's equal to approximately 2.718. Because e is an irrational number, these decimals technically go on forever. They'll never repeat or form a pattern. The line y is equal to e is an asymptote of the function y is equal to 1 plus 1 over x to the x power. Now, if you can't remember that, that's okay. All you really have to remember right now is that e is a special number, just like pi is a special number. We typically use e in exponential growth and decay problems when we need to demonstrate continuous exponential growth or decay. The most common type of exponential growth and decay problem that is continuous is a continuously compounded interest problem. Here we're given the formula for a continuously compounded interest problem. This is a is equal to p times e to the rt, where a is the amount we have at any given time, p is our principal, or the amount we first invest, r is our rate of interest, and t, of course, is time. So now let's try a continuously compounded interest problem. Here we're told that Billy has $500 to invest. If Billy invests his money for 10 years, should he invest it in an account that is compounded annually at 5%, or in an account that is compounded continuously at a rate of 5% per year? Well, first let's look at the one that's annually compounded. For an annually compounded interest rate, we use the standard exponential growth formula. Our amount is equal to our principal, the amount we first invest, times 1 plus our interest rate raised to t. Now the amount we're going to end up with is equal to our principal, which is 500, times 1 plus our interest rate, which is 5%, so 1 plus 0.05, all raised to the t power, or the 10th power. So our amount is going to be equal to 500 times 1.05 to the 10th power. So our final amount in our annually compounded account would end up being $814.45. So now let's look at the account that's compounded continuously. Here we're going to use the formula a is equal to p times e to the rt. Our amount is equal to our principal, which is 500, times e to the 0.05 times 10 power. So our amount is going to be equal to 500 times e to the 0.5 power. Now 500 times e to the 0.5 is equal to $824.36. So while they're very close, Billy would be better off investing in the continuously compounded account. Now let's look at a second example involving continuously compounded interest. Here we're told that Jim's grandmother opened a savings account for him 18 years ago. If the account earned 3.5% interest and is currently worth $1,877.61, how much did Jim's grandmother initially invest? Well, since we're dealing with continuously compounded interest, we're going to use the formula a is equal to p to the ERT. Our a is what we're given. It's $1,877.61. This is going to be equal to our principal, which is what we're looking for, times e to the r, which is 3.5%, or 0.035, multiplied by our time, or 18 years. If we simplify this, we'll have 1877.61 is equal to p times e to the 0.63 power. So we have 1877.61 is equal to p Now e to the 0.63 power is 1.8776. If we divide both sides by 1.8776, we're going to find out that Jim's grandmother invested $1,000. So that completes this continuously compounded interest problem, and it also finishes our tutorial on the natural base e.